Hi all, in this video we will discuss about PCIe enumeration process. Before going into the topic, let's understand some basic concepts. This is called host bridge, which connects CPU to the PCI topology. It can have many bridges. These are called virtual bridges, virtual PCI bridges. The bus inside the host bridge which connects various PCI virtual bridges to host bridge is called bus number 0. These are called switches. Switches are logical assembly of one or more PCI bridges. These are again virtual bridges. It has one upstream port and more than one downstream ports. So mainly it is used for connecting more than one PCI device to one PCI bridge. Now we have discussed buses and the links are PCI link is created between two PCI devices. Here this is one PCI link, this is one PCI link, it's one PCI link, all these are PCI links. This is PCI, and that this particular thing is PCI to PCI bridge. The buses inside switches or host bridge are the buses which are not of PCI, so it's internal to switch, but we consider it as one bus. In PCI topology we can have up to 256 buses, and each bus can have up to 32 devices, and each device can have up to 8 functions. When we say 32 devices, these 32 devices on one bus is possible only inside host bridge or switches, or maybe on PCI bus, not on endpoints across PCI link. We see here only one device is connected to one bus. If we talk about this particular bridge will be connected to this particular bus, and this endpoint is connected to this bus. So in PCI bridges we have configuration space where we define primary bus, secondary bus and subordinate bus. So primary bus is the bus number where upstream port of that particular bridge is connected to. Secondary bus number is the downstream port which is connected to this bus. Number secondary bus is 9, so it means it is connected to 9 bus. Subordinate bus number 9 means the farthest bus number in this particular hierarchy. Here 9 is the farthest bus number, so secondary and subordinate bus numbers are same. Similarly, let's consider example here. Here we say that primary bus is bus number 0. So this particular PCI bridge is connected to bus number 0. Its upstream port is connected to bus number 0. Downstream port is connected to bus number 2. So secondary bus is 2. Subordinate bus number is 5. So in this particular hierarchy, the farthest bus we can have is 5 here. So it means subordinate bus number is 5. Okay, so here each bridge or endpoint function has configuration space. It has its own configuration space. All these bridges has its own configuration space. Similarly, host bridge will have its own configuration space. So all the function, like it is one device but has two functions, both have their own configuration space. Configurations, we can have two types of configuration transaction which we discussed in last video. One is type 1, used to interact with the configuration space of bridges, and type 0 for accessing configuration space of endpoint devices. CPU initiates the configuration transaction by writing in the configuration space of host register and some IO registers that we will discuss. After that, host bridge converts this transaction into type 1 transaction. Let's suppose that there is transaction CPU wants to do on bus number 5, device 0, function 0. For that, CPU will write in IO registers in host bridge. Now host bridge will initiate type 1 transaction. This transaction will follow this path. When it will reach here, as soon as bridge sees that this transaction is for bus 5 and subordinate bus number is also 5, so it will convert into type 0 transaction for this. Okay. After understanding these concepts, let's move to enumeration. What is enumeration? When system comes out of reset, all PCI links are established between PCI devices. All these links will be established. But CPU doesn't know how many PCI devices are connected to it through host bridge. So enumeration is a process of detecting all the PCI devices connected to the host bridge and their location. When I say location, location means on which bus number this particular device is connected. Here, this device can be identified by bus number 9 and device 0 and function 0. So here one thing we should understand, there is no register which writes that this endpoint is connected to bus number 9. So so we understand that this particular endpoint is connected to bus number 9 by the bridge, which says that secondary bus number is 9. And so first point of enumeration is detecting the PCI devices and its location. Now I would say second point is understanding the features of the device. So depending upon the feature of the device, like some devices could be network controller, memory controller, CPU loads the driver and initiates the transaction. So for that also CPU needs to initiate some configuration read transaction for the configuration space of that particular device. Number 3 is each device may have some memory space inside it. So this memory, if CPU wants to access that memory, it needs to map this memory to the system memory. So mapping of device memory to system memory, so that we can access this memory. Sorry. So enumeration process is detecting of PCI device and its location, understanding the features of the device, mapping the device memory to the system memory. So in this, today we will understand that first 2 points, and in separate chapter we will understand how memory of a device is mapped to the system memory. Okay. Again, process of detecting PCI devices connected to CPU, initiated by CPU on power on, assigning address of the device, and this address based on ID bus device function, memory base and address are mapped with the system memory, and understand the features of the device. After initiating or completing these 3 steps, CPU has the complete understanding of the device, and accordingly it can initiate the transactions. Okay. So for all this, for the enumeration process, CPU needs to read the configuration registers of bridges or endpoint devices, and we say that PCI and PCI Express are software compatible, so its register space need to be same. So first 256 PCI has 256 bytes of register space, and PCI Express also uses 256 bytes. It has more registers to add more capability, but 256 bytes are must. Out of these 256, 64 bytes are configuration headers, which can be of type 0 or type 1, and 192 bytes are capability registers. So these are used for having more capabilities, like for PCIe it should have MSI capability. These are interrupts, power management, and PCI capability registers. Okay, we discussed that out of 256 bytes, 64 bytes of PCI configuration space makes the configuration header space, and it is different for type 0 and type 1. Type 0 is for endpoint, type 1 is for bridges, out of which some registers are obsolete and not used for PCI Express, so like we don't need to bother about them, like these registers. These are for not required. Okay, so similarly this card CSI CIS pointer is not required now, and out some more registers are required for mapping the endpoint memory to the system memory. Similarly these registers. Oh, sorry. So all these registers we will discuss in the next chapter. So here this vendor ID is defined by the PCI SIG. It is unique ID for each vendor. Combination of vendor ID, device ID, vendor ID, and class code. It is class code, subclass code, and then peripheral register peripheral address makes the feature of the device, like if it is mass storage device or graphical controller or network controller, after reading device ID, subclass, class or class code revision ID, we know that which divider need to be loaded for this particular device. Similarly, for subsystem vendor ID and subsystem ID is also required. Like here, device ID is for chip maker and subsystem vendor ID and subsystem ID is for that card maker. We discussed earlier that bridges has that configuration space in which we configure primary bus number, secondary bus number and subordinate bus number. So this we configured here. And in 192 bytes are capability structure. In previous slide we saw that for PCI Express we should have MSI interrupts, power management and PCIe capability registers configured. So from configuration space we can go through capability pointer. Capability pointer contains the start address of, let us suppose, MSI. MSI is here, so this is the start address which will be configured in that capability register. So here again we will have some address which will point to power management, and again here we will have address which will point to PCI capability registers. Or it may be like first it will be PCI capability register, capability pointer will point to PCI capability register, or then power management or MSI. So it is kind of linked list. Okay. So earlier we discussed about that configuration space which is common between PCIe and PCI Express, but PCI Express has more configuration space called extended configuration space, and each PCIe endpoint can have up to 4 kilobytes of configuration space. Here we can see that 256 bytes are PCI compatible configuration space. Okay, so 64 bytes are PCI compatible configuration space, and up to 256 is that capability pointer. So this is PCI and PCI Express should have these both. Out of this, here we have that PCI Express capability structure in which we discuss MSI, power management and PCI capabilities should be there, and for other features we have the memory space which is up to 4 kilobyte. So how CPU initiate that configuration transactions? So this is a configuration access mechanism. PCI compatible. PCI and PCI Express both uses this same process to initiate the configuration transaction. So here this is our CPU, host bridge, let's suppose that in host bridge we have one PCI bridge, host bridge is here, we have PCI bridge, and PCI bridge is connected to the endpoint device. So host bridge has configuration space which is configuration type 1. Endpoint has, this is bridge, host bridge. Endpoint has configuration space which is type 0. Here it is connected through bus 0. So for initiating the transaction to endpoint, CPU writes initiate the IO transactions. This is called IO indirect transaction. So there will be addresses here which is CF8 and CFC. So these two transactions, CPU initiate two transactions on these two addresses. Then if a host bridge sees these transactions on these addresses, then it will initiate type 1 transaction, and from this bridge it will be type 0. So what is those addresses where the CPU writes? These are IO addresses. And what it writes? On CF8 it writes the location where transaction need to be routed, and this at this address it writes the location where transaction need to be routed, and this address is written in terms of bus number, device number and function number. So we know that we can have up to 256 buses starting 0 to 255. So on which bus number we need to initiate the transaction? Bus number will come here. Device number, if it is endpoint, so we will have only one device, and function number we can have up to 8 function number, 0 to 7, device can be 0 to 31, and register number. So in every function we have the configuration space. For accessing the configuration register, in the configuration space we write the register number here, and last two LSB bits are 00. It means granularity is 4 bytes, and 31st bit need to be set to enable the configuration space transaction. So this particular configuration need to be done at CF8. Now is it's write or read depends upon if CPU reads or write this particular address CFC. If it's write something here, so it means configuration write transaction on what? The address which is written in CF8, which in terms of bus number, device number and register number. If it is read transaction, first CPU will write that bus number, device number, function number, BDF in CF8, and then it will read from CFC. Then host bridge will initiate the configuration read transaction. Okay, so we saw that CPU writes at address CF0 and CF8 and CFC to initiate a configuration read or configuration write transaction. Once CPU writes, then host bridge will initiate that configuration transaction. It converts that particular read or write into this particular transaction format. Here it tells that it is configuration transaction when it is 1. If it is 0, it is type 0 transaction, 1 when type 1 transaction, and here format tells that it is read or write transaction, here bit. So we know that okay, if it is read transaction, it will be the bit in the format will be 0. If it is write transaction, it will be 1. So whatever bus number, device number, function number are written at address CF8 will come here, and register number will come here. And we know that configuration transactions are of one word, so length will be 1, and it is one word. So first word it will be, so first double word, which byte we want to read, accordingly this double word byte enable will be set. Last byte enable, because we are using only one double word, so this all last byte enable will be 0. Traffic class will be 0 for configuration transactions, and all these fields are not required. AT attribute we can just ignore, they all will be 0. Okay, let's understand the configuration access example. Let's suppose that CPU wants to initiate a transaction to bus number 10, device 0, function 0. So how it will be done? First CPU will write here at CF8 bus number, device number, where bus number will be 10, device number will be 0, function number will be 0, and it will enable the bit number 31, so that it says that okay, this is a configuration transaction. Now if CPU wants to write, what it will do is it will write the data in CFC. Once these transactions are seen by host, what host will do, it will create that configuration transaction and send it to bridges, or it is internal implementation specific. This transaction will be passed to bridges. Now bridges application layer may create that configuration type 1 transaction. Why type 1? Because we have already configured the configuration space of bridge, in which primary bus number is 0, secondary bus number is 7, and subordinate bus number is 10. So it has secondary bus number 7 and subordinate bus number 12. We want to initiate transaction on bus number 10. So from here, configuration type 1 transaction, type 1 read transaction will be initiated. Type 1, config type 1. So write transaction will be initiated. It will reach here, which will say that this transaction is for bus number 10. It sees that okay, bus number 10 is in its hierarchy because it is less than a subordinate bus but greater than secondary bus. So bus number 10 transaction will route downward. Here it will be seen that okay, here we have primary bus number 8, secondary bus number 9. So bus number 10 doesn't exist in this hierarchy, so it will not pass through here. Here it will say that okay, secondary bus number is 10, so it means we are initiating transaction for 10, so it will reach here. Now it will see that secondary bus number is 10 and subordinate bus number is 10, and we have initiated transaction for bus number 10. Here this particular bridge will convert configuration transaction type 1 to type 0 write transaction. Now this transaction will be accepted by the endpoint and configuration space will be written. But here we are seeing that we need to initiate 2 IO transactions for each configuration. 2 IO transaction means first we need to configure the address at CF8, and then we need to initiate read or write transaction at CFC. So we have to initiate 2 transactions to initiate one configuration transaction. So multiple CPU in multiple threading system, there might be some race condition, like first CPU writes at CF8, before it initiate the transaction to write on CFC, another CPU may initiate transaction on CF8 again. To avoid this condition, we have another way to configure or initiate the configuration transaction, that is extended configuration access mechanism. In that mechanism, we know that each device, whether it is bridge or endpoint, has 4 kilobyte of memory space, configuration space. So if each endpoint or bridge has configuration space of 4 kilobyte, then from BDF we have up to 256 buses, which comes out to 2^8, and we have devices in each bus. We can have up to 5 devices with 2^5, and each function can have up to 8. Each device can have up to 8 functions, so which will come out to be 2^8 plus 5 13 plus 3 16. And each function, these are number of function, each function can have up to 2^12 bytes of configuration space. So 2^28, which comes out to 2^56, megabytes. So it means if we can have up to 256 megabytes of configuration space in PCIe hierarchy. So if we map the base address to the system address, then each 4K can be corresponds to each functions on bus, like bus 0, device 0, function 0, and bus 1, bus 0, device 1, D0, function 1. So this memory space can be up to 256 megabytes. So it will be base address or start address plus 256 megabytes. Now if CPU wants to initiate any transaction, any configuration transaction, then only one configuration transaction on is required instead of two. Let's suppose that base address is 2000 and we want to write that bus 0, device 0, function 0. Then from 2000 to, if CPU initiate any transaction on 2000, host bridge will automatically map this transaction to the configuration transaction for bus 0, device 0 and function 0. So again here we have base address. If we calculate that, this will come out to 27 down to 20 will be base bus number, after that device number and function number, register number. Okay, let's understand the enumeration through example now. We know what is enumeration and how CPU initiates that configuration transactions, and now we need to know how CPU completes the enumeration. Okay, first step, CPU will write in the configuration space of host bridge for secondary bus and subordinate bus. It will write secondary bus as bus 0. We know that the downstream port connected to bus is the secondary bus. Subordinate bus is the bus number which is farthest away in that hierarchy. So in the starting, CPU doesn't know the subordinate bus number, so it writes here the maximum possible bus number which we can have, and that is 255. So in the starting, software writes secondary bus as bus number 0 and subordinate bus as bus number 255. Now CPU initiates the transaction for bus 0, device 0. How it will initiate? There are two ways. One is that IO indirect and another is the extended memory access. Using these two any of that, CPU will write bus 0, device 0 and function 0. So on bus 0, this transaction will go to device 0 and function 0. In host bridge, device numbers will be hard coded. So it is already hard coded that this is device 0, this is device 1, device 2, device 3 and device 4. And when CPU goes for enumeration, so here we does the depth first search. Depth first search means, like here it is going for device 0, it will go until it find the last device in this particular hierarchy Once it finds, then it will go to find the last device in this particular hierarchy. If it is calculated, then it will go here, then it will move to next device. Okay, so we discussed that first CPU writes that prime secondary bus number and subordinate bus number to 255. After that, it initiated transaction on writing IO registers, which is at CF8 or CFC. It writes the bus number, device number, function number, and after that it reads at address CFC. Once it reads, then configuration read transaction is initiated on bus number 0, device number 0. That type 1 transaction will reach to PCI bridge and it will read its device ID, sorry, vendor ID. If vendor ID read is all 1, it means no device is present. If it has some number, it means PCI bridge is available. After reading this bridge, it will configure its, it will read its header. There is one header register which tells that we forgot to discuss earlier. Header register tells that it is multi-function device or single function device. Or single function device. If it is single function device, it is called phantom function. Or it also tells, is it endpoint or bridge. So first header will be read. From there it will know that so first vendor ID will be read. If it is all ones, it means this particular bridge is not configured. If it has some value, it means this particular bridge has that is available. Then it reads its header. Once, depending upon header value, it knows that it's endpoint or bridge. Once it knows that it's a bridge, then it configure its primary bus number, which is 0. Secondary bus number will be 1, and subordinate bus number it will configure it as 255. So next step will be initiating a configuration type 1 transaction for bus 1, device 0 and function 0. Again, same steps will be involved. First, it will read the vendor ID. If it is all 1, it means no device is connected. If it is, because how it will be all 1? When CPU will initiate transaction for bus 1, device 1, 0 and function 0, this transaction will not pass through by the bridge, and it will get some errors. What error it will get, that we will discuss in separate section when we will discuss about errors. Once it gets the error, then it sends all ones. It means saying that no device is connected. So first it reads the vendor ID. After that it will read the header register. In header register it will know that okay, it is single function device and it's an endpoint, not a bridge. Once it is read, then once CPU knows that okay, it's a endpoint device, then it will again write the subordinate bus number to 1 instead of 255. So primary bus number, secondary bus number and subordinate bus number for this particular bridge is configured by CPU as primary bus number 0 because its upstream port is connected to bus number 0. Secondary bus number is 1 because its downstream port is connected to bus number 1. Subordinate bus number 1, it means that the farthest bus in this particular hierarchy is the bus number 1. So after configuring this, CPU will initiate transaction for bus 0, device 0 and function 0. Here again device vendor ID will be read. If it gets all 1, it means this particular bridge is not configured. So if it gets some other value, it means this bridge is configured. Then it will read its header register. After reading its header register, it will know that okay, it's a bridge, not a device. Now it will configure its register in which primary bus number will be 0, secondary bus number will be 2 because 1 is already taken here. This is bus number 1, secondary bus number 2 and subordinate bus number. Still we don't know how many buses are there in this hierarchy, so CPU will configure it as subordinate bus number as 255. And we should remember that still here 255 bus number is configured in this configuration space. Now same process will be initiated again. I told that it is depth first search. Until we don't complete the hierarchy here or all the endpoint devices connected, we will not move to next device in the host bridge. We have configured primary bus number, secondary bus number and subordinate bus number in the PCIe bridge. Now CPU will initiate a transaction on bus number 2 and function number 0. Again it will read the vendor ID. The vendor ID is not all 1, it means some device is present. Then it will read its header register. In the header register it will check that okay, this is not endpoint, it's a bridge. After that it will also check its phantom function or multifunction device, and next will be it will configure that subordinate bus number to 255. Here it will configure 255, here it will configure again 255, just assuming that all the buses are in this particular hierarchy. This bus number is 3 because primary bus number 2, here upstream port is connected to bus number 2. Secondary bus number is 3 which is connected to downstream port. Subordinate bus number is 255 at present. In the largest bus number is 255, which is farthest away in this hierarchy. Now CPU will initiate a transaction on bus 3. This is bus 3, device 0, this will be device 0 and function 0. Now again it will read its vendor ID. Once vendor ID is read, then it will read its header. After reading the header, it will know that it's a bridge. Then again it will configure its register for primary bus number, which is 3. Secondary bus number should be 4, which is down. This is up downstream port, and subordinate bus number 255. Okay, it will consider that all the buses up to 255 are on this particular hierarchy at present. Now again CPU will initiate a transaction on bus number 4, device 0, function 0. It will read that function in header. First it will initiate to read vendor ID. If it doesn't get all one, it means device is connected. After that, it will read its header. In header, bit 0 will be bit 7 will tell that it's a multifunction device and function 0 is available. Once function 0 is available, then it's a device driver responsibility to scan all the functions. So we can have function 0, function 3, 1 or 2 we may not have, might not have functions. So if we find that it's a multifunction device, then CPU should initiate transaction for all the functions. So for function 0, it will understand the feature of the device or properties of the device, or function 1 again it will understand the properties of the device. Now we know that bus 4 has endpoint connected to it. So this bus number 4 is the farthest away bus in this hierarchy. So subordinate bus number will be updated from 255 to 4. Again, CPU will go back to the switch and now initiate the transaction for bus number 3, device 1, function 0. Here again it will read the vendor ID, then header will tell it's a bridge and phantom function. After reading it, it will configure the primary bus number 3, which is connected to upstream port, secondary bus number 5, which will be connected to downstream port, and subordinate bus number at 255. Again, CPU will initiate a configuration transaction for bus number 5, device 0 and function 0. Here again it will read vendor ID. If vendor ID is correct, then it will initiate a configuration type 0 transaction to read the header. Header tells that it's a phantom function or not, and it's an endpoint device. Once it is done, or after reading more configuration and configuring, then it will go back and configure the bridge to subordinate bus number 5 instead of 255, because bus number 5 is the farthest away bus number in this particular hierarchy. So here farthest bus number is 5 and here farthest bus number is 4. If we go one hierarchy up, so it will say the farthest bus number is 5. Now CPU will initiate bus 0, device 0, device 0, 1, 2, device 2 and function 0, and reads its vendor ID. If we get all 1, then it means no bridge is configured. But it may be done in future, so we leave a device which may get connected in future, and we make it a device number bus number 6, device 0, function 0. Now host will initiate transaction on bus number 0, device 0 and subordinate bus number 0, device 0 and function 0. Again, host will read that it's a vendor ID is available. After that it reads its header to know that it's a endpoint device or bridge, and its phantom function or multifunction device. After reading it, it configures the primary bus number to 0 because it is connected to 0, secondary bus number to 7 because earlier device may connect to bus number 6 to device 2, and now we discussed about that bus number, device number and function number. Function number is normally 0 in the bridges. So now here CPU will first read the vendor ID, then it will read that after reading vendor header, and after reading header it will configure that sub primary bus number which is 0, secondary bus number which will be connected through a downstream port which is bus number 7, and subordinate bus number it will configure earlier for 255, considering that all the hierarchy is available here. So this transaction will reach to, now CPU will initiate a transaction on this particular bridge. First it will read the vendor ID. If it gets the vendor ID, it means it is connected properly, and then after reading the vendor ID it will read the header register. In header register again it will tell it's a bridge. Now transaction will be passed to bus number 8. In bus number 8 we will have primary bus number is 8 which is connected to the upstream port. Secondary bus number is 9 which is connected to downstream port. So after that CPU will initiate a transaction on bus number 9, device 0, function 0. Okay, before that we have discussed that here bus number is 8, secondary bus number is 9, and subordinate bus number will go to 255. Okay, so now CPU will initiate a transaction on bus number 9, device 0, function 0. After initiating transaction, then CPU knows that this is the farthest bus, so it converts this 255 to the farthest bus, which is bus number 9. Once it is done, then CPU will initiate a transaction for bus number 10, device 0, function 0, and the host bridge will have primary bus number as 8, secondary bus number as 10, and subordinate bus number as 255. After this, CPU will initiate another transaction on bus number 10, device 0, function 0. Once, then again it will read its vendor ID, then header type that tells its endpoint, and once it knows that its endpoint, CPU will change that 255 to bus number 10, which is subordinate bus number. Now we will move to primary bus number 8, secondary bus number 11, subordinate bus number as 12. So here subordinate bus number will be again configured 255, and this will be passed to bridge PCIe Express to PCIe bridge. Here primary bus number is 11, secondary bus number is 12, subordinate bus number is 12. So how it does? Again, first here bridge vendor ID will be read. Once vendor ID is read, header will be read. In header we will have that how many functions there are, and what is that bus number, device number, function number, what is the which is used for mapping the or routing the transaction configuration, type 1 or type 0 transactions. Here we have written primary bus number as 8 because it is connected to 8, secondary bus number as 11 because 10 bus is already used, and subordinate bus number as 12. Subordinate bus number as 12 means the subordinate bus number will be 255, means the last bus connected to this hierarchy is 255. Now CPU will initiate transaction for primary bus number is 11, secondary bus number is 12, and that subordinate bus number, it will configure it as 255. Now CPU will initiate the transaction on PCI bus. Now on PCI bus, we know it's a parallel bus. We will have device 1 function 0, device 2 function 0, and device 3 function 0. And once it is known that it is PCIe device and all are connected, so here then it will be converted from 255 to 12, because 12 is the subordinate over secondary bus number here, and 11 is the primary bus number. Once it is done, we know that okay, subordinate bus number is 12, not 255. Similarly, now we will configure that bridge for subordinate bus number at 12 instead of 255, and now this bridge will be configured to as primary bus number, subordinate bus number as 12 instead of 255, and this transaction will move here. Again, secondary bus number will be configured as 255 instead of 12. Now CPU will initiate a transaction on bus number 0, secondary bus number as bus number 0, with that device 0 function 0. We'll read the device vendor ID. If it doesn't get any other than 111, it means no device is connected in the bridge. So after this process, all the configuration space in the bridges is configured with primary bus number, secondary bus number, and subordinate bus number. And all the devices, all the transaction can be reached to any device using bus number, device number, and function number. So this is the process of detecting the devices and finding its location with respect to CPU's enumeration process. Here we are also finding its property by reading the configuration space completely, so that proper driver can be loaded. Okay, I think I skipped one step or lost. So now on bus 0, device 4 function 0, we read the vendor ID. If we don't get it, means this particular bridge is not connected. Now it will go back to that configuration space where we configured configuration subordinate bus number as 255. But now we know that the maximum bus number is 12 in this particular hierarchy, so it will change it to secondary bus number as 0 and subordinate bus number as 12. Thank you all for watching this video.